Okay. Again, now let's step through one more here. So we have 2 ethane and 7 oxygens. We're looking at a combustion reaction. Okay. And it says we want to produce 10 grams of water. All right. And it's telling us that we want to know how many moles are here. Okay, again, we have a gram value there, so I know I'm going to need the molar mass of water. I'm going to just put it in parentheses so it's ready when I need it. And again, on this table, I'm going to use this again as a teaching example. If I were actually solving this problem, I would really only need to fill out 2 columns of this table, the one for the ethane and the one for the water. But I'm going to kind of step you through, use this because it has lots of different coefficients, but I'm going to kind of talk you through what the approach would be with these. Okay, so B, C, A. All right, my zeros are going to be on my products and on my reactants. Okay, and I want to end up with 10 grams of water. So now here in this one, the thing that's different is they're giving me a value for a product. When they give me a value for a product, that's going to be what I want to end up with, which means it's going to go in the after position. So if I have 10 grams divided by the molar mass, that's going to be 0.555 moles of water, which means my change was plus 0.555. Okay, so now, all right, let's just take a look at how are we going to get from there to the ethane. Well, it says for every 2 moles of ethane, I get 6 moles of water. So I get 3 times as much water. The change in the water should be 3 times the change in the ethane. So I can, and I'll just write it out here to remind you where this number comes from. So that divided by 3, right, is going to give me 0.185. So that is, and it's going to be a minus because it's a reactant. All right, so there's my moles. That was the change, which means I started with 0.185. Okay, and I know this, for some of you, this will seem like a really simple process, but I promise you, if you go through and make it a habit of using this table, one, it's gonna make limiting reactants a lot easier for you. And when we get to the equilibrium, that's going to be easier for you as well. And it is a really nice way to get you thinking about what's happening, what it is that you're calculating. Okay, and I like that because I know just from my own personal experience in college, it is very possible to factor label, get the correct answer for a problem, and really not understand what you were calculating, because factor labeling, you're just manipulating units. And you can get really good at manipulating units on lots of stuff and calculate values where you really just don't understand what is the process that you are modeling with your calculations. So I like these tables because it at least gives you a format to really kind of see what is happening and what you are calculating. All right, so now let's look at where would we go next if we were going to fill out the whole table. Say we had questions about everything. And so one of the things I wanted to point out in this situation is, even though the 0.555, the change in the water, was the first thing that we calculated, that doesn't mean that we have to ratio everything else off of that. Choose values that make the math easy, okay? So if I wanted to look for the change in the CO2, all right, rather than doing the 4:6 ratio between the water and the CO2, that 2:4 ratio will be much easier math, right? Because that tells me the change in the carbon dioxide is going to be twice the value of the change in the C2H6. And so this one, it's going to be positive because it's a product, and it's just going to be 2 times 0.185 is the value that's going to go in that CO2. So that's going to be 0.37 moles, which means I would end with that many moles of the CO2. Now for the For the oxygen, and we don't really have any place that's nice and easy math for that. And so for that one, when you have a situation like that, you just go back to a ratio, and we can do it with any of them. So let's pick the ethane. So C2H6, 2 moles of that to 7 moles of oxygen. All right, and the change in the C2H6 was 0.185. And so I'm solving for what the change in the oxygen would be. And so I have 7 times 0.185 divided by 2. So 0.648, that's a minus, okay, which means that's how much I would have needed to react with the 0.185 moles of the ethane in order to produce my 0.555 moles of water. So now I've got that table filled out, and again, if any question they ask me quantitatively about this reaction, I could then use this table to answer. Okay, one more. So on this one, we need to balance our equation first. That gives an unbalanced equation. So I think this one, if I remember correctly, 4 aluminums and 3 oxygens give me 2 aluminum oxides. And it says, it's another one where they're giving me a product. So it says I'm given 10 grams of the aluminum oxide. And so I know that grams is there, so I'm going to go ahead and calculate molar mass for aluminum oxide. So it's around 102 grams per mole. All right, and it wants to know moles of oxygen. Okay, so this one, I'm going to go ahead, I'm going to do this one the way you would do it if this were the problem and this is the only thing that they're asking you. All right, so CCA, all right, 0 on the product for the before line, 0 on my reactant for the after line, and I'm going to get my moles of aluminum oxide, 10 divided by 102, that's 0.098. So the change, I want to end up with 0.098 moles, and so the change was plus 0.098. Okay, it's a 2 to 3 ratio between aluminum oxide and oxygen. All right, so I'm going to just set up that ratio real quickly. So I have 3 moles of oxygen to 2 moles of the aluminum oxide. And if I have 0.098 moles of the aluminum oxide, oxygen, okay, so I solve that. 3 times 0.098 divided by 2. So 0.147, so I'm going to put that down there, 0.147, and again, just as a reminder to you, what we get out of that ratio, this is moles of oxygen, that's the change. So it's going to be minus because oxygen's a reactant, 0.147, all right, which means I would have started with 0.147 moles, and that is the answer to the question. Okay, there will be a follow-on podcast from this on using this table format with limiting reactants, and hopefully, especially those of you that have tried to do limiting reactants other ways, hopefully you will be able to see the value of this format in solving limiting reactant problems.